In this video, we are going to talk about something called continuity. Informally, we say that a function is continuous at x equals c if the graph is unbroken at x equals c. So here are three ways that the graph of f of x might be interrupted or broken at x equals c. By the way, these breaks in the graph are called discontinuities. So one way is that f at c might be undefined. So imagine a function that looked like this. All right, it's swooping down, but then right at c, we find that the function is actually undefined. So this is a discontinuity. It's a break in the graph. Another type of discontinuity occurs when the limit as x approaches c does not exist. So remember, for a limit to exist, the function has to approach the same value from the left and from the right. So you can see that from the left, the function is approaching a certain value. There's a certain y value here. But imagine that from the right, the function is approaching a different value. This would be a break in the graph. It would be a discontinuity. The third way a graph can be broken or interrupted can happen even if the limit as x approaches c does exist, and even if the function is defined at c. Let's draw a function like this. So first of all, let's make sure the limit exists. So as we approach c from the left, we're going to be approaching this value, all right, this y value. And then as we approach c from the right, we are still going to be approaching that same value. So far, the limit does exist. The only problem is, the way I have it drawn right now, the function is undefined at c. Well, I can fix that by putting a point right here to represent that this is the value of the function at c. So now the function is defined at c. The only problem is the limit as x approaches c and the value of the function at c are not the same thing. So that is another way that the graph can be broken, is if the limit as x approaches c does not equal the actual value of the function at c. You get this little jump right here, which is a break in the graph. This is a discontinuity. Avoiding these three types of interruptions to the graph leads us right to the definition of continuity. A function f of x is continuous at c when these three conditions are met. Number one, f at c has to be defined. That will help us avoid this type of interruption. Number two, the limit of f of x as x approaches c has to exist. That will help us avoid this type of break in the graph. And finally, number three, the limit of f of x as x approaches c has to equal the value of the function at c. And that will help us avoid the third type of interruption to the graph. Before we move on, I need to add these two words to your vocabulary. Discontinuities can be categorized as either removable or non-removable. The reason why we call this type of interruption in the graph removable is because we can repair the break in the graph just by defining f at c properly. So in this case, if I just decide that f at c is going to be right here, I'm just going to define it that way, then that will fill in this break in the graph, and we have removed the discontinuity. All right, we go from being undefined to now it's defined. I've defined it to be right here. Let's skip over to this other one. This one is removable Because right now, when we start out, the value of f at c is defined to be way up here. That's just the wrong place. That leaves a break in the graph. So all we have to do is redefine f at c to be down here. So if we just say, never mind, the value of f at c will not be up here, we're just going to decide that f at c is going to be down here. So that will take this away and fill in the break. So now we have removed the discontinuity. The reason why this middle case is non-removable is there is no value where you can define f at c that will fill this gap. No matter where you put your dot, all right, because f at c is really only going to cover a single point. There's no value of f at c that is going to fill in this gap. That's why this is called non-removable. So let's just write that down formally. Removable versus non-removable discontinuities. A discontinuity at x equals c is removable if defining f at c properly will make the function continuous. Let's discuss the continuity of each function, starting with f of x equals 1 over x. Now, 1 over x is defined at every value of x except for 0. So there's definitely a discontinuity. It's just a matter of what kind. Let's picture the graph of 1 over x. We know the graph is going to look something like this from our past experiences in other courses. All right, so there's this asymptote here. So is this going to be a removable discontinuity or a non-removable discontinuity? There's definitely a non-removable discontinuity at x equals 0. There's no way to define f at 0 to make the function continuous. In other words, there's no single dot that I could put on this graph that would fill in this gap. What about g of x, which equals x squared minus 1 over x minus 1? We know that the graph is undefined at x equals 1. So there's going to be some type of discontinuity at x equals 1. The only question is it removable or non-removable? Is it an asymptote or is it a hole? So let's factor this to see what's really going on. X squared minus 1 can be factored, difference of two squares, x plus 1 times x minus 1. Notice that we have x minus 1 in the denominator. So if I want to get a look at the shape of this graph, I can cancel out the x minus 1s. When you cancel out a factor in the numerator and denominator like this is when you get a hole in the graph. All right, this is what it looks like when you're going to have a single missing point in the graph. So if I want to think about what the graph of the function looks like, I can just focus on the remaining part of the graph. So imagine just graphing y equals x plus 1. What would that look like? All right, obviously this would be a straight line and with a y-intercept of 1. So here's 1 right here. The slope it has a slope of 1. So we're talking about a graph that's going to look something like this, except for at x equals 1, that's where the discontinuity is. So let's be careful. If when x is equal to 1, that's where the function will be undefined. So let's mark that value on the graph. So here's where x equals 1. So I'm going to continue my line, but when I get to here, I'm going to have a hole in the graph. So we have a removable discontinuity at x equals 1. If we define f at 1 to equal 2, then the function would become continuous. So if we let f at 1 equals 2, that would fill in this gap right here. All right, well, what about the function h of x, which equals x plus 1 when x is less than or equal to 0, but it will equal x squared plus 1 when x is greater than 0. So we've got this nice piecewise function. We really need to do a graph so we can see what in the world is going on. So the first part of the piecewise function basically tells us what the graph will look like on the left, to the left of the y-axis. So let's think about, first of all, what's happening right at 0, because it will actually be this first piece of the function when x equals 0. So this is a good place to start. Well, if x is 0, then I have 0 plus 1, so the value of the function at 0 will be 1. So I'm going to go ahead and indicate that on my graph. So here is a value of 1, and this will be one point that is on the graph. Now, as I go to the left of 0, the graph will look like the graph of x plus 1. This is a straight line with a slope of positive 1 and a y-intercept of 1. So if I were to graph this entire line, it would look something like this. But it's only going to be this graph left of 0 or equal to 0. So we can forget about this part right here. And this is what the first piece of the piecewise function will look like. Now, what about the second piece of the piecewise function? All right, for any value greater than 0, this is the function that will be graphed. So even though it's only going to apply greater than 0, we have to start by asking ourselves, what is happening at 0? And if it happens to be in a different spot, then we'll just simply do an open circle. Say if it happens to be up here, we'll just put an open circle to show that it doesn't start at 0. But let's see what happens. If we let x equal 0, if I substitute 0 in for x right here, 0 squared is just 0. So I have 0 plus 1, so the value is going to be 1. So right at 0, this expression has a value of 1, which picks up right at the same spot where we left off. So there's no point in me putting an open circle here because there's already a point filled in at that same position. So I'm just going to go on and imagine what the rest of the graph would look like. I know that the graph of x squared, for example, is a parabola. All right, we all know that x squared is going to be a parabola. X squared plus 1 is just going to be a parabola that was shifted up 1. We know this as well. So that's what's happening here. We just have a parabola that's been shifted up 1 unit. So that's what the right-hand side of this piecewise function will look like. From here on, it's going to be a parabola that was shifted up 1. So here is the whole graph. Notice that the function is defined at every value. So there's no problem there in terms of discontinuity. Notice that even at the questionable spot where we change from one piece to the other, the limit as x approaches 0 is 1 from both sides. So as we approach 0 from the left, we're approaching a y value of 1. As we approach 0 from the right, we're still approaching a y value of 1. So there is no discontinuity here. So we can say that this function is continuous everywhere from negative infinity to positive infinity. What about y equals sine x? Let's look at the graph. We know what sine x looks like. Sine x looks something like this. It's a periodic function that just goes up and down forever. And it does the same thing to the left and to the right. So the graph is uninterrupted. There are no values at which the sine of x is undefined. There are no discontinuities. We can say that this function is continuous everywhere from negative infinity to positive infinity.